All right, we're going to start talking about coordination complexes. And before we get into the nomenclature of coordination complexes, let's talk a little bit about what they are. And first, let's talk a little bit about how normal ionic complexes dissolve in solution. So if you have something like sodium chloride, when you dissolve it, you dissolve 1 mole of sodium chloride, you get 1 mole of sodium plus, 1 mole of chloride minus. If you dissolve 1 mole of calcium chloride, you get 1 mole of calcium, 2 moles of chloride. So this was one of the first things, and this was in the 1880s and 1890s. There was a whole set of different complexes of cobalt that could be orange, purple, green, or violet that were composed of cobalt with chloride and with ammonia. And we had an orange compound that has this empirical formula, and when dissolved in solution, 4 ions were released in the solution, and this solution contained 3 free chlorides. Next, there was the purple compound, which has this empirical formula. When it was dissolved in solution, there were 3 ions in the solution and 2 free chloride ions. And then, strangest of all are these last two, which have the same empirical formula, but clearly very different colors. These both produce 2 ions when they're dissolved in solution, and they both contain 1 free chloride ion. So Alfred Werner in 1893 proposed this type of structure for these complexes. He proposed that we have a complex cation. In this case, we have a cobalt-3 center with 6 ammonia ligands attached to the cobalt-3 center. And this is floating around in solution. This is a robust molecule that's floating around, molecular cation that's floating around. And then we have 3 free chlorides. So these we often will refer to as counterions because these are just there to balance the charge. They're not interacting directly with the cobalt at all. They're simply there to balance the charge. And most of the time these could be changed out. So these could be changed out for bromides or nitrates without changing the fundamental chemistry of the cobalt center. So here is the orange compound. Now we know the structure of it, and the structure is in fact correct, what Werner said. And let's see what would happen if this was dissolved in solution. So if it's dissolved in solution, we would get the cobalt 3 plus cation plus 3 chlorides. Okay, that's a total of 4 ions per formula unit. And 3 free chlorides. Okay, these chlorides are not attached to the cobalt, so those are free. If we add something like silver in, we'll very rapidly replace the chlorides with nitrates if we were to add silver nitrate to this. All right, let's look at the next complex. So the second formula that we have here, the purple compound, Werner's structure for it would be this one that we've drawn here. We have this complex cation. It has a 2 plus charge because it's cobalt 3. Chloride has a minus charge. So the charge on the whole complex cation is 2 plus. Plus 3 minus 1 gives me 2 plus overall. Well, let's see what would happen when this dissolved. We would get this large complex cation, that's 1, and then 2 chlorides. So 1, 2, 3 gives me 3 ions per formula unit. And then it says that there's 2 free chlorides. So these chlorides that are outside the coordination sphere are free. These could be removed with silver nitrate. But this one, which is bound to the cobalt center, is actually bound to the cobalt center, and so it's firmly attached, and it's difficult to remove. Okay, these last two are perhaps the most interesting in the fact that we have the same formula, we have the same number of ions, we have the same number of free chlorides, but we get 2 distinct different colors. And let's see what happens here. Well, this was the best part of Werner's hypothesis. So he proposed that the green complex has a cis orientation. The two chloride ligands are as close as possible in the coordination sphere. And so this is one arrangement. Or the chlorides can be far as possible in the coordination sphere. If we have them close as possible, we get the green complex. If we have them further apart, we get the violet complex. And let's do our final analysis here. When this is dissolved in solution, we get 2 moles of ions, the complex cation and the simple anion for either of these. And we have 1 free chloride. So this free chloride is the one that's just floating around in solution, the counter ion. The 2 that are bound to cobalt are not free. These are more difficult to remove. So if we added a bunch of silver nitrate to this one, we could replace chloride that's out here with nitrate, but it would be more difficult to replace the chlorides that are attached because they're firmly attached to the center. So here kind of summarizes what we see. So this is the usual case that we'll have a central metal cation with some ligands around it, and very often it will have a positive charge. And then out here in pink we have a counter ion, and this is simply there to balance the charge. So we'll have however many we need in order to balance all this charge out. We can also have just complexes, and a complex is neutral overall. So the overall charge of the metal plus the ligands is neutral, and so then there's no counter ions, and so it's just it hanging out in the solvent solution. So complex, this is a complex cation.